So the topic of my talk is probably slightly different from the rest of talks today. It's the future of Mars exploration, specifically how are we going to get humans on Mars. And so I'll talk a little bit about the motivation behind why we do explore our solar system and specifically why we do explore Mars. And then I'll talk next about the path forward to eventually get people to land on the surface of the planet. And so this very first picture, of course, is an artist's conception of what the surface of Mars looks like, but we've collected many images over the course of the past 20 years or so that validates what we think the planet looks like. But just a little bit of a background on me, so you understand why I came here. So my training is all in aerospace engineering, my bachelor's, my master's, and my PhD. I worked for most of my career for NASA's Jet Propulsion Laboratory, which is one of the NASA centers which focuses on the robotic exploration of space. I started off actually working on a mission called the Dawn mission, which is currently out in the main asteroid belt, working on the propulsion systems for it. And so one of the reasons why we travel to deeper into our solar system, specifically into the main asteroid belt, is we take a look at asteroids which tell us about how our solar system originally formed. So what does the inside of our planets look like? Worked on that for about 5 years, and then taking one step in, I worked on a mission called the Mars Science Laboratory Curiosity Rover mission, which is the bulk of the talk that I'm here today to give. And that is where we sent a very large rover to the surface of Mars to understand how the planet Mars evolved. Then after that, I worked a little bit closer to Earth, putting up a station experiment on the International Space Station to understand sort of how the universe first formed by looking at the concept of fundamental physics. And now I'm currently working on the development of the hyperloop, which is a new form of transportation, which very much uses spacecraft technologies, but here at home to improve problems and challenges that we have. And so the reason why this is all relevant is that we need only take a look at the planets closest to us. The planet in the middle is Earth, the planet off to the left-hand side here is Venus, and the planet to the Mars is to the right. And what's interesting is that at the formation of our solar system, these planets were very similar to each other. They actually had water on the surface, they had an appreciable atmosphere. But over the course of the past 4 billion years or so, Earth, of course, is still a wonderful planet, we live here today, Mars is very cold. It has a temperature of, the coldest temperature you could find on Earth is the warmest temperature you can find on Mars. It has no appreciable water on the surface and has a very thin atmosphere, about 1% of the atmosphere that we have on Earth. On the other hand, you have Venus. Venus is one planet in from us. Venus has a surface temperature of 475 degrees centigrade. That's very hot, right? No organisms can survive in that kind of temperature. And it has a surface pressure 100 times Earth's surface pressure, which means that over the course of the past 5 billion years, our planets have evolved, which means that climate change is a planetary phenomenon. We can see that in our own solar system. So when we explore planets like Mars, planets like Venus, and we compare them to Earth, we actually learn about how our own planet is evolving. That's really important now more than ever as we recognize that climate change is starting to impact our daily lives, is starting to impact our own selves as well as all the other organisms on Earth. But at the same time, science is very interesting, and specifically solar system exploration is very interesting. And Mars is a very interesting target because as we go out into the stars, we want to be able to find other planets that we can one day live on the surface. And Mars actually isn't so bad. It's actually better than our moon because it does have an atmosphere. It's better than our moon because it has resources available to us that we could even use to create oxygen on the surface. So Mars is a little bit smaller than Earth, which means it has lower gravity. So obviously that's not good for human beings, but there's still a portion of gravity there. It also has an atmosphere which is primarily carbon dioxide. So if you can come up with a way to split the carbon dioxide, you can generate oxygen, which you would need for people to be able to live there. It does have an appreciable atmosphere on the surface, which means you could pump it into your chambers to get you up to atmospheric pressure, which you could survive in. It does have a very cold temperature, generally, but in the middle of the Martian summertime, in the equatorial regions, in the middle of the day, the temperature actually can become something which is sustainable to life in that sense. So of all the planets in our solar system, Mars is the most likely place that we could one day colonize and have people living on the surface. And the final element, of course, is that the Martian day is actually very similar to the Earth day. And that means our circadian rhythms, which control whether or not we're asleep or we're awake, won't be too affected by the fact that we would one day potentially live on Mars. But the other reason why Mars exploration is so interesting is because Mars has had a very interesting geological history. So if you take a look at the image on the left-hand side here, this is called Olympus Mons. This is the solar system's largest volcano. It's the largest mountain in the solar system. It's 3 times the height of Mount Everest. So that means at some point in Mars's past, it experienced volcanic activity. But nothing has happened, as far as we know, from a volcanic activity perspective, in several billion years. So what happened? How did the planet evolve to have huge volcanoes, massive eruptions, and now nothing for billions of years? Similarly, Mars, going across the center of the planet, has a feature called Bellus Marineris. It's about 6 times as deep as the Grand Canyon. And for those of you who are fans of geology here on Earth, the Grand Canyon was formed by water flowing on the surface. So at one point in the past, Mars did have pretty significant water flows. But what happened to the water? Where did it all go? Where did the atmosphere go? The way you answer those questions is by actually sending spacecraft to orbit the planet and rovers and landers to land on the surface of the planet. And so one potential theory of what happened to Mars is that long ago there was an asteroidal object which impacted the planet, disrupted its core, disrupted its magnetic field, and then in-space radiation took the atmosphere away and left the planet to where it is today. And so that's a hypothesis. And the way you actually test a hypothesis is you do an experiment, and the experiment in this case is sending spacecraft to orbit the planet as well as land on the planet. And interestingly enough, we have a spacecraft called the Insight Spacecraft, which is going to land on the surface of Mars at the end of this month, actually. And it's being set up to take measurements of volcanic activity on the surface, very weak sort of Mars quakes that we might find, and that will help to test that particular hypothesis. And another really interesting aspect of Mars is that it actually does have moons. These moons are very small. They're not like Earth's moons, which means that they haven't yet turned into a spherical object because of their own gravitational differentiation. But these moons are natural satellites. And what that means is that you could put telecommunication systems on these moons and use these to one day support a telecommunications infrastructure on Mars so you can communicate between Earth, the moons of Mars, down to the surface, right? You don't even have to have your own GPS network. You could use these moons for that purpose. We also know that these moons have a signature on them that suggests that they contain water and other minerals. So for a future human exploration of Mars, these moons can be used for communications relay stations, but they could also be used as a source of raw material for building, as well as for water to eventually bring down to the surface of the planet. So I'm trying to change your way of thinking of utilizing the resources that you have around you. So by a show of hands, who thinks that we've found water on the surface of Mars? So we actually have, several times now. So this picture that you see here is of the Phoenix lander, which landed in the early 2000s. And underneath the lander, you see this white patch. This white patch is actually frozen salt water ice. During the landing event of the Phoenix rover, its engines were pluming into the ground, and what they did was they exposed the ice layer just beneath. And so those little drops that you see on the left-hand side here, we were able to see them evaporate. And based on the rate at which they evaporated, we were able to tell that they were actually made of salt water ice. So we know that in the polar regions of the planet, there's actually a significant amount of water which is frozen in the subsurface. Why is that important? You could use that water for growing plants. You could use that water in order to basically wash yourself and potentially turn it into something that you could drink. So there are resources just beneath the surface on the planet which could be used for a future human colonization activity. What's even more interesting is that there's actually flowing water on the surface of Mars today. This is a relatively recent finding, 2016. We have a spacecraft which orbits the planet called the Mars Reconnaissance Orbiter, which takes higher resolution images of the surface of the planet, which is where all these images come from. And so what you can see in the upper right is black streaks. Those black streaks are actually wet mud coming out of the sides of cliff faces on Mars. What you see on the lower left here is also another side of a cliff face, seasonal flows of wet mud on the surface of Mars. So this means that because the planet is tilted on its axis, it heats up and it cools down during the course of its transit around the sun. So when it heats up, any water which is frozen in the subsurface comes out, seeps out of the sides of the cliff face, and is something that could potentially be used for a future human colony. And even more interesting, where there is water, there is often life. There could potentially be organisms in this water. And so we haven't yet had the chance to send a rover to these locations, but we hope to one day. And the other really interesting thing about this, and in general about the space program, is that all the data that's collected is essentially open source. That data is there for anybody to analyze, whether or not you live in Sri Lanka, whether you live in South America, whether you live in the United States, whether you're a student in high school, a student in college, or just a citizen scientist. All this data is available for you to analyze and look at and draw your own conclusions, which I think is interesting, because the software community, I know you're shifting over to open source, but the scientific community has always been open source, and that means that people together can actually understand what's going on at a planetary scale, as opposed to doing it for personal, private, financial reasons. So by a show of hands, how many people think that humanity has landed on the surface more than 5 times of Mars? Okay, so you guys are not as big Mars buffs as others. So we've landed on the surface a total of 7 times to date. All of those landings were done by the US space program, NASA, but as we move forward as a society to explore space, we're going to have to do this together and work with all the different space agencies. But way back in the 1970s, the Viking landers landed on the surface of Mars successfully. That's pretty fantastic, right? Because think of the state of computer technology in the 1970s, right? Your iPhone that you have today, or your smartphone that you have today, is probably 4 orders of magnitude more powerful than the computer technology that was available in the 1970s. So it is kind of amazing what we can do now relative to what we had back then when it comes down to the hardware or firmware side of things. So there was about a 20-year period in time where nobody actually went to the surface of Mars. It was only in the 1990s when interest was brought back up again, and we developed the Pathfinder Sojourner rover, which was about the size of a Tonka truck, a small child's toy. Move forward another 5 years, we landed the Mars exploration rovers on the surface, and then in 2012, we landed the Curiosity rover on the surface of the planet. And now we have 2 more missions coming up, the Insight rover lander, which is coming at the end of this month, believe it or not, so I hope you guys can pay attention to the news and you can actually follow it real time. And we also have the Mars 2020 rover, which is going to be launching in 2020, which is going to collect even more scientific data. And what's so amazing from these images, this one from the Viking lander, this from the Sojourner rover, this from the Mars exploration rovers, is that the landscape on Mars looks eerily similar to a desert landscape on Earth. And there's a reason for that, because the terrestrial planets are so similar to each other. We have this similar ancient history from the formation of our solar system. So for us to be able to live there one day as a species is something that we can do if we develop the correct technologies. But from an engineering perspective, it's actually very difficult to land something on the surface of another planet for a whole variety of reasons, which I'll talk about. But what you can see in this image is that over the course of the past 30 years or so, the space program in the United States has evolved its technologies, starting with this tiny little rover, which is about, yay big, shifting over to a rover which is the size of a lawnmower, which is the Mars exploration rover, Spirit and Opportunity, and then shifting to a rover which is the size of a small car and the same weight as a small car. And the reason for that is because these missions are scientific missions. And so part of a scientific mission is to carry scientific equipment. The larger your wheelbase, the more equipment you can carry. And so the larger the wheelbase, the more difficult terrain over which you can transit, the more interesting scientific data that you can get. Scientific data that scientists care about to understand the planetary evolution, but scientific data that we all care about so we can figure out where could a future human settlement be based off of the data that we collect. But we evolve our understanding of our technologies, we evolve the sophistication of our landing techniques because we do this once every decade or so. We land again on the surface of the planet. So the purpose of the Mars Science Laboratory and Curiosity mission was to understand whether or not Mars could once have been habitable or support life, and whether or not the planet still can do so today. And so that was done with a combination of different scientific measurements, specifically looking at how did the rocks form. Were they formed in water? Were they just formed volcanically? What is the radiation level like on the surface? Can human beings or can any kind of organisms exist in those kinds of radiation levels, either in the past or currently? And also to understand the role of water in terms of forming all of the surrounding geology that you see on the planet. And so those were the hypotheses that we wanted to be tested as a course of this mission. My role on the mission, of course, was on the engineering side. I worked on the side to land the large rover on the surface of the planet, and I'll talk a little bit how that worked in a few minutes. But the most important thing is that where do you want to put your rover? You want to put your rover in a place where you can learn the most interesting scientific information. So if you were an alien species coming to visit the Earth, would you land in the middle of the Sahara Desert, or would you land in the middle of the Amazon rainforest? You would land in the middle of the Amazon rainforest because you're most likely to find interesting scientific information. Of course, on Mars, we don't have the benefit of landing in a rainforest, right, because it's a relatively inhospitable environment, but we do know that there are places on the surface of the planet that once contained water, and so we selected a place called Gale Crater, which you see on the lower right-hand side, because it was believed to be the source of an ancient water body a long time ago, billions of years ago. So we selected this location to land, the scientific community did, and then it was the responsibility of the engineering team to put the rover down safely in this regime. And then just for some reference, MSL, Mars Science Laboratory, landed in Gale Crater, and our prior mission, the Mars Exploration Rovers, landed all the way over in Meridiani, which is very far apart. So the two can never actually meet each other, because there's no way they can climb out of the craters that they're in to meet each other. But it's a large planet. The more places that you can interrogate across the planet, the more scientific information you can actually learn. But this particular landing site was very challenging. And the reason why it was so challenging is because this elliptical shape you see here is our prediction of where we believe the rover would land based off of a whole variety of different parameters in terms of aerodynamic performance of the vehicle, how the environment would be on a given day, wind speed, density, temperature. And so it occupies a space of about 7 kilometers by 20 kilometers. So we had to have a landing accuracy of that in order to be able to land safely. If not, you would either smack into the side of the crater wall or smack into the middle where you have a large mountain, which is about 6 kilometers high. So that was the challenge, is being able to land something which is, many hundreds of billions of miles away in an area which is quite small. And so for scale, I put a small portion of Colombo, so you can get an idea of sort of the level of accuracy which is required from planet Earth to a tiny little region like this. Is basically a region the size of your downtown of Colombo, is a level of accuracy that you have to have. And so that happens to be an engineering challenge. And this graphic shows you how that engineering challenge has been dealt with over the course of the past 30 years. So this very outer ellipse was from the 1970s, an area of roughly 200 kilometers in the length of the ellipse. We've shifted this all the way down to an area of only 20 kilometers in the maximum length of the ellipse. So we've got basically an order of magnitude improvement in our landing accuracy over the course of the past 20 years. And that improvement in landing accuracy is what allows us to go to this very interesting scientific location, both to understand how the planet evolved, as well as to understand what kind of environment would a future human colony find itself in, and how can we design a system to keep people safe from that perspective. And then just to give you a little bit better scale, this is basically Sri Lanka. And so the long or the wide axis of the country here represents the landing accuracy back in the 1970s, whereas the distance between downtown and the airport, or in Negombo, represents the landing accuracy that we approved to over the course of the past 30 years. And so that's what's necessary to be able to go to one of these locations. And of course, the next challenge, the next level of difficulty, is that if you're going to land people on the surface of Mars, you have to reduce that landing accuracy to on the order of meters. So that's even more difficult, obviously, right? Because you'll have to land them closer to where their food supply has already been established on the surface of the planet. So how do we land a system like this? So we do it through a combination of technologies. So what you see here is something called an entry vehicle. Inside of this is the rover. It comes into the atmosphere at around 13,000 miles per hour, or 20,000 kilometers per hour. Aerodynamic drag actually slows it down. When you get to around 1,000 miles per hour, deploy a very large parachute, which slows it down to around 250 miles an hour. At that point, you've hit terminal velocity on the parachute, and you cut the parachute away. The rover now, you can see here, is in free fall, but it has a series of 8 engines just above it which are firing into the ground to slow it down even further to get to around 2 miles per hour. When you get to a height of about 20 meters or so above the surface, the rover starts to get lowered on a set of 3 tethers. And it continues to descend this way until the rover actually touches the ground, the wheels touch the ground, it senses that, and those tethers are cut. And the spacecraft above is then tilted 45 degrees and flies off to the side a safe distance. So that is the landing system that we implemented to land the Curiosity rover on Mars. It does seem very complicated, and it is very complicated, but you require that level of complexity to be able to land something that large with the level of accuracy that we needed to be able to land in this location. The advantage of this landing system versus other landing systems that you might be familiar with from the MER days with airbags is that it allows your rover to be the lander, right? So you land wheels down and you can go off and start your mission. And so that was a very challenging engineering feat, but it was a very interesting one in terms of an engineer working on the program. And so we did that in August of 2012. So to take a step back as to what are the technologies involved, the entry vehicle containing the rover is basically an airplane. It looks like a very strange airplane, and I like to say it's a bird in this sense, since I was trying to figure out what the local wildlife is, but a bird operates on the principle of aerodynamic lift. Our entry vehicle also operates on the principle of aerodynamic lift, and so this ugly-looking bowl shape generates a lot of drag, which is good because you want to slow down, but it also generates lift. And what that does, it allows you to fly in a controlled fashion down to your landing site on the surface of Mars. Now, the other thing that this entry vehicle has on it is it has a series of engines on the backside which allow you to roll the vehicle, which then allows you to modulate where that lift vector is to fly more precisely to your landing location on the surface of the planet. So this was the very first time that this was attempted, and it was done so successfully, and that flight was all done autonomously. There's no human being in the loop. So all of this done with closed loop guidance, navigation, and control, which means with onboard flight software based off of the information that it's detecting in terms of its altitude and its speed as it approaches the surface. So very much so in the case of a autonomous entry, descent, and landing system that you see here, software coupled to measurements of speed and altitude is what enables you to land something so large and so heavy with that level of precision, because it's essentially in an airplane. So this is another view of what this system looks like. This is a two-dimensional view. So what I showed you before in that video is you are literally coming in with an orbital velocity of around 13,000 miles an hour or 20,000 kilometers per hour. But what's so nice about Mars is that Mars actually has an atmosphere, which means that if you're going down the highway and you put your arm out, you feel the buffeting force on your arm, right? That's aerodynamic drag. As this vehicle enters the Martian atmosphere, it experiences aerodynamic drag and it slows down. And it does so interacting with the atmosphere, which then unfortunately ends up generating a lot of heat, but you use a different technology called a heat shield to be able to protect the rover within it from getting too hot. So you eventually achieve terminal velocity using that drag area, and then you have to deploy a parachute. The parachute has to be incredibly large, so the parachute that we built for our mission basically occupies twice the size of this room. And the reason for that is because the atmosphere is so thin, so you need a much larger drag area. Once again, you hit terminal velocity, then you have to come up with another way to remove even more velocity, which is where we use retro rockets to get yourself down to the ground. And so that's the overall entry, descent, and landing sequence that we developed for this mission, and it was successful. And the reason why that's important is because what we learned from the success of this feeds directly forward to the next set of missions, and eventually feeds directly forward to landing a human-sized payload on the surface of the planet. So, one relevance to what you guys are doing here is the waterfall versus agile methodology. And so traditionally in aerospace, you do follow the waterfall methodology, but for the entry, descent, and landing system architectures, we have to do a lot of prototyping and testing where we do iterative design to be able to get something that actually works. And so this is non-traditional for aerospace, but it's necessary for something which is this sophisticated and this complicated. So you can start to see how there's a segue between the two different communities. And then the other unique aspect of this mission is that we were able to use computer simulations to make predictions of performance. So my particular role on the mission was designing the Supersonic Parachute, and we were able to develop physics-based computer simulations that told us how the parachute would behave. This actually shows you what the flow field around the parachute is like, how it would perform in terms of its aerodynamic drag, how it would perform in terms of how strong it needed to be able to survive that environment. And we were able to use computer simulations instead of guess and check to come up with the design of this technology, as well as a range of other technologies that were used for this mission. And so you really can nowadays, because of the advent of supercomputers, use software to design a lot of your engineering hardware. And that's done certainly in aviation, commercial aviation, and it's also being done on things for the space program. So just to take it back to the real world in terms of the hardware development, this is the parachute system that we developed and tested. This, of course, is an Earth-based test. So after a lot of design work, a lot of computer simulations, we were able to verify that we had a parachute that could survive the environment that it would see on Mars by doing a test here on Earth. So you do always have to do prototyping and testing, right, in hardware as well as in software. And then, not to get too messagey on you, but it's really important in all the things that we do that we have teamwork and that we have diversity in our teams. And this is something which is important to me because I'm in a field which is historically a male-dominated field, not a lot of women in it, and even in my team, there was one woman in it. But the thing is we had people from all over the world, all different backgrounds, all different disciplines, working together to be able to create a system that worked. And so teamwork is really important. And the antithesis of that is the example from the Matrix, right? Where you have one person who thinks the exactly same way, who does the same thing, perhaps with a random number generator, but that's the end of it. So you do need teamwork and you do need diversity to actually come up with innovative solutions to challenging problems. And so that seems like a no-brainer, but it's something that we should all strive to do in our place of work. So the future. So what is in the future? So as part of the Mars Science Laboratory Curiosity mission, we were able to test out a bunch of new technologies which we need for all future missions to explore Mars. The first one was an advanced power system. So one of the challenges that we had with our prior rover technologies is they relied on solar panels. Solar panels degrade over time, and specifically on Mars, where there's a lot of dust in the atmosphere. Dust deposits on the solar panels, and then they can no longer generate enough energy, and eventually the rover will die. And sadly, that happened very recently to the Opportunity rover, where it was caught in a global dust storm, and we haven't been able to communicate with it since, unfortunately. So most likely the rover did not survive that, purely because it had too much dust on its solar panels, it couldn't generate enough energy, and it couldn't keep itself warm. So for our most recent rover, Curiosity, we had on board a nuclear power source. So something called a radioisotope thermoelectric generator, which generates its own heat due to plutonium-238 radioactive decay. It generates heat to keep itself warm, but it also converts that heat into electricity, so it's its own onboard power source. So with the demonstration of this technology, with the Curiosity rover, we can implement this on all future missions to Mars, as well as missions which will carry people on the surface of Mars. And it allows it to be very robust in terms of it can operate over a larger range of latitudes, and it also allows it to operate over a longer portion of the day, and it allows it to stay operational for many, many decades with almost no change in power. So that's an example of a new technology that we were able to implement on this missions. But in order to understand the planetary science aspect of this mission, you have to carry a series of instruments. And those instruments include many things. One of them is to detect the composition of the atmosphere. Another one is to detect the composition of rocks. Another one is actually to make measurements of the wind and the temperature and the pressure variations over the course of the day. And then one of the most important ones, though, is the ability to have an arm to reach down, to grab soil, to grab rocks, and to put them inside of the instrument to be able to make more detailed measurements of it. And so this particular rover carried that entire suite of instruments on board to make those scientific measurements. And my very favorite one is the LIBS instrument, Laser-Induced Breakdown Spectroscopy. It doesn't look as extreme as this, but it actually has a laser on board that fires between my distance to basically the wall of the screen there. It burns a hole in a rock. When the rock is burnt up, it releases a vapor, and by looking at the spectroscopic signature of that vapor, you can determine what the rock is made out of. And so it's a very sophisticated way of making measurements of composition of materials such as rocks and soil that we see on the surface of the planet. So the big challenge, I think, for sending people to Mars is that you have to be able to stay in space for a relatively long period of time. And so our mission was launched in November of 2011. It only took actually 7 to 9 months, which is the gestation period of a sloth and a gestation period of a sloth bear, which I guess is resident in Sri Lanka. So 7 to 9 months isn't that bad, right? It's actually the course of a school year. It's the course of 2 semesters in college. So if you can tolerate a length of period like that, then you would be able to make the transit to Mars as a future human occupant on the surface of the planet. And so we did launch in November of 2011 on a launch vehicle. Took us about 8 months to get there. And we had a very unique opportunity in this mission, which was to have a camera on the underside of the rover looking down towards the ground. And so there's several reasons for that. One is because it's really interesting, right, to be able to see what you're looking at as you get down towards the ground from a PR perspective. But there was a real engineering reason for it, which is to collect image data, eventually do image processing on that data to do terrain relative navigation on the next mission. So this is the technologies that we put on one mission, we use to facilitate a new way of landing on a future mission. So in this video, what I'll show you is the view from landing night looking down towards the surface. So what you're seeing here is the heat shield dropping away, and this is the rover looking down towards the surface of Gale Crater. And so what you see are some dark regions. These are ancient volcanic deposits. You also see a lot of pockmarks on the surface, which are basically evidence of micrometeorites going through the atmosphere and crash landing on the surface, because the atmosphere is very thin as compared to Earth. What you also see is a rocking motion back and forth. That's because the rover was sitting under the parachute during this portion of the descent. And so you see this oscillatory motion. So the engineering team gets to take this data and back calculate out, how did the parachute perform? Does it give you the same oscillatory motions that we thought? And we can actually use that engineering data to improve our models, to improve our trajectory design for the next mission. So really shortly what you'll see is the rocking motion stops, and it starts to veer off to the side. At this point, the parachute has been cut away. We're now descending towards the surface on those retro rockets. And so you're going to see us getting closer and closer towards the ground as we're descending. And eventually the sky crane maneuver, which is the lowering on the rover on the tether, is going to start to come into view. Those rocket engines are now firing directly into the ground, which is kicking up a bunch of dust. Now you see the rover's wheel come into view, and it's descending towards the surface. And eventually you can't see anymore because basically you've blocked out all the light. So this is the data that we were able to collect using an onboard camera, which in future missions will use this plus an algorithm to determine how far we are away from our target location on the surface of the planet for terrain relative navigation. So that entire sequence, of course, was done autonomously without a human being in the loop. And the reason for that is obvious, is because Mars is very far away from Earth, so the time delay, due to the speed of light limitation, is on the order of 7 to 14 minutes. And that entire landing sequence takes only 7 minutes. So it actually lands before you even know that the sequence even started. So it has to be done autonomously. But after landing on the surface, the rover was required by its flight software to send an image of its landing location. So what you see here is the shadow of the rover, and then Mount Sharp in the distance, which was that mountain in the middle of Gale Crater. What you see here is a color version of the same landing location. And it's just so fascinating how similar Mars looks to Earth. So if you've ever been to the desert, in Nevada, for example, in the United States, looks just like this. So even though it's the surface of another planet, it looks like our own, which always kind of blows my mind in that sense. So it's pretty exciting. Now, from the engineering team's perspective, of course, it's fantastic, right? Everything worked, but we wanted to know how good our calculations actually were. And so what you can see here on the bottom is a red ellipse. This was our engineering prediction of where we thought the rover would land as a function of variations in wind speed, density, temperature, aerodynamic performance of the different components of our vehicle. And we landed in that white box right there. So it's pretty close to the center. So which means our calculations were good, they were conservative, and our system performed as intended, which was landing inside of that red ellipse. And then from a larger looking out perspective, where the rover landed, was still pretty far away from where we eventually wanted to do our scientific measurements, which was the base of Gale Crater. So it has to drive a really long period of time before it could get to that location. And that's unavoidable because there are some things that you just don't have control over. So if you had landed right next to there, that's fantastic. But as long as we landed within that box, we would spend a certain number of months driving to the location that we wanted to get to. So for me, as the person responsible for the parachute system, I of course was interested in how the parachute performed. Obviously, everything in that landing sequence is single string, which means if one element fails or if one element doesn't perform at its nominal level, the mission doesn't work. So from the parachute's perspective, we had the unique opportunity to position the Mars Reconnaissance Orbiter spacecraft, which is an orbit around Mars, to a location so it could take a picture of the rover descending under the parachute on landing night. So that's what you see here. And so this was a very important picture, obviously, because it allows us to see the health of a parachute during descent on Mars in terms of, is it fully inflated? Does it have any damage? And it doesn't, obviously. So it performed as inspected. So these are the different diagnostic techniques that we have during the course of the entry, descent, and landing sequence to be able to see how well we did as an engineering team so that we can do an even better job the next time around, for example. So another key technology which is required for almost any mission that lands on the surface of the planet is fully autonomous systems. And the irony is that we're still in baby steps of having autonomous vehicles here on Earth, where we have control over all the parameters. But for the space program, we've always had to implement autonomous systems, because there's no way you could have a human being in the loop because of the time delay between those different locations. And so the rover has the ability to drive itself. So every single day, we communicate it with it twice a day. First time is to say, this is what we'd like you to do today, which is go over to this spot and make this series of measurements. And then at the end of the day, we communicate with it again to get the data back and see how everything went and give it the sequence for the next day. And so the rover drives itself autonomously, which means it has a series of cameras so that it can do hazard avoidance. And so all of this, once again, is done autonomously. If it sees a dangerous obstacle ahead, if it notices that there's a change in its attitude because the soil is too weak or something like that, it will stop to protect itself. So fully autonomous system. The very first time we tried driving it, you can see it driving in a circle, back and forth to make sure all the systems operated okay. But once again, it drives itself. We do not drive it with a joystick. So it is, in fact, an intelligent system. It may not be AI, but it is a very intelligent system. And in such a vein, it's able to take a picture of itself, or a selfie, because it has enough cameras that it can piece together a 360-degree image of itself. And so this always makes kids laugh, so maybe it'll make you laugh. So the rover has the ability to take a selfie, so it can, then several reasons for this, right? Number one, it gives you a pretty good idea of its landscape, but number two, it allows you to see what the surface of the rover deck looks like, to give you an idea of its health, for example, just from that perspective alone. And some of these jokes may not be good for here, but I'm a cat person. I do like cats. And so one of the reasons why we send rovers to the surface of Mars is to determine whether or not there is life on Mars. And although we are not able to determine today that there is life, we are able to make measurements of potential future habitability. And so one of the key instruments that we use for that is the laser-induced breakdown spectroscopy instrument, which is this laser which burns a hole in the rock. And so the picture you see here is a picture of a rock on the surface of Mars, and you can see the hole which is formed after the laser pulse is initiated. That simple act of burning a hole in that rock generates a vapor, which is then viewed in terms of its spectroscopic signature to tell you exactly what the composition is of that rock. So it's pretty sophisticated, repeated measurement, which once again is done autonomously. And that data gets sent back to Earth in terms of telling you what elements are present. And what we have found over the course of this mission for the past over 6 years now is that we have found all the building blocks of life. We have found all of the elements which are required to make organics here on Earth, we have found on the surface of Mars. So it's a very important finding from that perspective. Now, one of the most important measurements that have to be made to send people to Mars is to understand what is the environment like, and specifically, what is the radiation environment like. And so this is the first time this measurement has ever been made, which is there is a radiation sensor on board, and it made measurements of what the radiation levels were like on the surface. Now, the bad news is the radiation levels are quite high. They're higher than the allowable dose for an astronaut, so it means we have to do something about it, right? You can't have people going around on the surface of Mars without significant radiation protection on them, or buried underneath the ground so they're protected from it. But because we now have this data, we know how thick the radiation shielding needs to be. We know the energy, basically the spectrum, the energy spectrum of that radiation, so we can design a radiation shield. So by sending robotic missions first, we collect the data which is necessary to send future human missions to the planet. And then another interesting piece of information is that you can see that there's this cyclical dependency to the radiation signature. The reason for that is because the atmospheric pressure changes on a diurnal basis. During nighttime, daytime, the pressure is going up, the pressure is going down. So what this means is the atmosphere of Mars actually helps to attenuate the radiation environment on the surface, which is good news, right? It means that you could use something like a gaseous shield to protect you from the radiation environment on Mars. So now we know the information necessary to design the technologies to be able to send people to the surface of Mars. And then a similar measurement you see on the upper right, which is the variation in temperature on the surface of the planet. And that changes, of course, seasonally as well as daytime to nighttime, just as it does here on Earth. But this is our own weather station on the surface of the planet. And another very important scientific finding is that we have detected methane in the atmosphere on the surface of Mars. And that's incredibly important because methane is an organic molecule. Methane is only produced by geological processes or biological processes, right? The bacteria in your gut, you generate gas, that's methane, which means that the planet still is in some way, or very recently, has been volcanically active, or there's a source of methane from an organic source, which of course is super fascinating. So we know the planet itself, at least from a geological perspective, is relatively alive, which is pretty exciting. And if it came from a biological source, that's even more interesting. And what I think is a great corollary is the Indian mission to Mars that launched a couple of years ago is also making measurements of methane in the atmosphere from an orbital perspective. So all of this data we can put together, piece together to understand what's actually happening down there on the surface of Mars. So the future, of course, is being able to land people on the surface. And what I've talked about today was the challenge that we had to land something the size of a small car in the area of downtown Colombo. What we have to do to land people on the surface of Mars is something the size of a spaceship in an area the size of this room, right? That's even more complicated. And so the way we do that is with a new technology called terrain relative navigation, which uses image processing as you're approaching the ground, comparing it to known maps on the surface to hone in and fly the vehicle exactly to the landing pad that you want to land on. And so we demonstrated an aspect of this technology with this mission, which was the camera, and the images that were collected. And so for a future human mission to Mars, this has to be implemented. And we're going to demonstrate an even further capability associated with this with the Mars 2020 mission. So you move forward in steps towards the final thing you need to send people to the surface. And so sending larger payloads to the surface. So all of you, I'm sure, have heard about Spacex, which is a company that's looking at also going to the surface of Mars. There's going to have to be many commercial entities working together to have this happen. And so one of the other challenges is having propulsion systems which actually operate at above the speed of sound to decelerate you going towards the surface of Mars. So that's another key technology in order to landing larger payloads on the surface of the planet. Because when you send a rover, you're sending something, the size of a car. When you're sending people, you have to send, 5 to 6 people with plenty of water, oxygen, and food supplies to keep them safe, as well as radiation shielding. So that means sending something which is much larger in diameter and much heavier towards the surface of Mars in a shorter region. But good news, we're also working on that. And so this is the Orion Vehicle, which NASA is working on right now, which is going to take us, instead of going beyond low Earth orbit, going beyond the moon, and hopefully landing us on the surface of Mars. And so this vehicle can hold a total of 6 people inside of it, and it could eventually one day have people re-enter the atmosphere of Mars and land and live on the surface of the planet. So these are technologies which are actively underway now, at least at NASA, to be able to facilitate this. But another huge challenge, though, is being able to persist and survive on the surface of the planet. And this means an environmental control system. So this is very challenging, right? Because you don't have access to a water supply, you don't have access to an air supply, except for what you bring with you, which means you have to be able to operate in a closed-loop fashion and not exceed the resources you have available to you. And I would say humanity has probably done a pretty bad job of that, right, in terms of how we treat our own planet. So we have to figure out how to solve a lot of these environmental challenges at home before we can ever hope to send people to live successfully on the surface of another planet, because the challenge becomes infinitely more complicated. But nevertheless, it has to be done, it has to happen, and we have made pretty good inroads on this in the International Space Station in terms of having closed-loop environmental controls. In the image you see on the right here, there are many studies underway with people living in research stations in Antarctica and the desert to show how you can live in this sort of closed-loop fashion with a fixed amount of resources for an extended period of time. So those are different things that we can do, what we're developing on the International Space Station, as well as the research stations that we can develop on the surface of the ground. But of course, you wouldn't want to go to Mars and not be able to move around the surface, right? You're going to have one base, but you want to be able to drive from that base and visit other locations. And so you have to have surface mobility. But the radiation environment is going to be a challenge. It has to be a pressurized vehicle, and it has to have its own power source. So the development of radiation-tolerant, environmentally controlled surface mobility vehicles is also what is in the future of Mars exploration. But we do have that underway as well at NASA, where these are vehicles. This particular one is using electric motor technology. This one doesn't have an encapsulation on it, but there is another version of it that does. So this is an example of a vehicle that you could have on the surface of the planet if you did have a hermetically sealed cap on top of it, which could give you that surface mobility from your home station all the way over to the different places that you want to explore on the surface of the planet. So probably the biggest challenge, though, is how can we use the resources on Mars to help us for a future colony? Well, from a power perspective, we can have solar panels. If we have people around, we can clean off the dust, right, to keep them clean, so you have access to solar panels. So that is available to us, which is solar radiation. Of course, it's reduced all the way out of Mars. Radiation protection. We know that we can use lunar soil to protect us from the radiation. That's been demonstrated with the Apollo program. You can also use Martian soil to provide you with radiation protection. It's literally material between you and the radiation environment on the surface of the planet. So you can put yourself subterranean, or you could create a habitat on the surface which uses soil as radiation protection. Water. We know that there's water frozen in the subsurface, so as long as you could apply a way to melt the water and then bring it in with a pumping system, you could use that water to grow food, potentially to drink, and certainly for washing of things. You can also use that water to extract oxygen, and you can use that water to extract hydrogen. And hydrogen can be used for fuel, for example, for a Mars ascent vehicle to get back. Methane. Methane is CH4. You could make CH4 from the hydrogen in the water, from this carbon and the carbon dioxide in the atmosphere, and that methane also can be used for fuel to drive your vehicle around, or once again, for a Mars ascent vehicle to get off the surface. And the final one, of course, is the most important one, which is growing food. The challenge, of course, with Mars is that it doesn't have any appreciable oxygen, which means you have to bring oxygen with you. But there are plants that can be designed that use very little oxygen and primarily use carbon dioxide for photosynthesis, which then generates oxygen, which you could use for a future human habitat. And then, in my personal opinion, the biggest challenge of sending people to the surface of Mars is radiation protection. And in this graph, what you see here is, this obviously is a log plot, which means it's getting an order of magnitude worse with each bar that you go up. But 500 days on Mars is a very high radiation level. The 180-day transit to Mars, similarly high radiation level. 6 months on the ISS is several orders of magnitude reduced from that. So we have a large technology challenge that we have to overcome to be able to get to a radiation level which is tolerant for people to be able to survive. So the measurements that we made with Curiosity gives us the data point to design a system, but we still have to design that technology. And so we do a lot of that with simulations once again. But probably, at least for the in-space version, you've all heard of Star Trek, I'm sure. They always say shields up on Star Trek. So there's the shields up from, bad aliens that don't exist, I hope, right now. But there's also potentially using a magnetic shield to protect you from radiation. So there is something which is not at all science fiction about this, which means that probably the only way we're going to be able to shield ourselves from in-space radiation is by developing a magnetic field shielding technology. And you want to know why I know that's true? The only reason why we're able to survive here on Earth is because around Earth we have something called the Van Allen radiation belts. We actually have a magnetic shield here on Earth. The planet provides it for us, right? So you probably need to do something very similar, not on the planetary scale, but on the spacecraft scale, to be able to protect human beings from the radiation environment that they'll see during the interplanetary cruise transit to Mars. And then growing food on the surface of the planet. So this is a huge challenge. There's no way that you can bring all the food with you. You need to be able to grow your own field. And the way you do this is by having habitats which are underneath the ground, using the soil to protect yourself from the radiation, and then bringing in sunlight using, for example, fiber optics to be able to provide the solar radiation necessary for plants to grow. So this is ultimately the way that you can use the resources of Mars to be able to generate food, and of course you'd have to be vegetarian in these instances, to be able to survive on the surface of the planet. But these are all experiments which can be done, and once again, we have an experiment on the International Space Station called the Veggie Experiment, which has lettuce and other plants growing inside on the ISS in a microgravity environment, showing that you can indeed grow planets in a very different environment in space, for example. So this actually is much more difficult than the environment that you would see on the surface of Mars, because on the International Space Station, you have no gravity. On the surface of Mars, you have gravity. And it turns out that plants need gravity to be able to grow efficiently. Otherwise, they grow very inefficiently. So the experiments that we do on the International Space Station actually helps us to understand how we could eventually grow food on the surface of Mars. And then, of course, artificial intelligence. So human beings are very weak compared to metallic objects or compared to any kind of robotic system that we would have. And so if we can have robots do as much of the work for us, whether it's heavy lifting, whether it's erecting habitats, before we ever get there, that's the way to do things, right? As opposed to sending people there to do all of the labor work, you'd actually want to send robots to do that ahead of time. So that, I would say, is a pretty good description of where we're at right now and the key technology areas to facilitate human exploration of Mars. It's not going to happen next year. It's probably not going to happen in 5 years, but it does have a very good likelihood of happening in the next 10 to 20 years, which is all within our lifetimes. That also comes down to sufficient funding, and it comes down to actually space agencies around the world working together to make that happen. No single space agency is going to make this happen. It has to be basically an international, global endeavor to facilitate something like this happening for our species. And to bring it back to home, though, is that before we do that, we do need to solve our own challenges here at home in terms of protecting our environment, in terms of coming up with ways to be green and have zero carbon footprint in what we do. Because if we can't do it at home, how could we possibly do it on the surface of another world, right? So I think it's all of our jobs in our respective fields to make that happen. And then I'll take questions for the remaining couple of minutes. But the really interesting thing is that in order to make these missions happen, even in the example of the mission that I worked on, which was Curiosity, is it takes a community of people. It takes biologists, it takes chemists, it takes aerospace engineers, electrical engineers, computer scientists, all distant disciplines in order to make this happen. If you're going to create a new colony somewhere, imagine what you'll need. You need doctors, artists, musicians. It takes an entire village or community of explorers to make these things happen. And the really exciting part, I think, about the space program is that all the data that we collect actually goes into the public domain. It's open for anyone to look at. Maybe not all the engineering design details if it's owned by a particular private company, but certainly all of the different scientific information that we collect is in the public domain. And I do personally think that we should have even more of the engineering information go out into the public domain so that we can work together to make this happen as a reality. So, thank you, and I'll take questions for the rest of my time that I have available. Okay, that's good. So the question was how, as individual developers, can everyone contribute to space exploration as opposed to just people working at different NASA centers or ISRO or things like that? So I think that's a really good question, and I don't think that the approach has been taken to date, where we were talking about this earlier about open source from the engineering side. I think that should happen. What does happen is that NASA, for example, puts out announcements of opportunities where you can actually compete to be able to get funding to develop technology in different areas, so propulsion technologies, autonomous system technologies, new ways to do modeling. So you can compete for funding to be able to do that, but it's still driven by some initial announcement opportunity from NASA. I know ESA does the same thing. I don't know if ISRO does that. I know that JAXA does the same thing. So that's a way that you can actually, part of your research as a university student, you can actually compete for that funding. But how could the software community? So I could give you an example. So one example is that the top speed of the rover right now is about this fast. It's very, very slow. And the reason for that is because it has to do all of these hazard avoidance measurements with images, and its computer processor is megahertz speed. Because space computers, or space-rated computers, are old. They're ancient technology. I mean, they're decades old. And so because of that, we're limiting the speed of the rover because of this old technology. So if the commercial sector could come in and generate a radiation-hardened computer technology at the gigahertz speeds, all of a sudden it would facilitate things. So if there are places where there could be some kind of dual use for a commercial entity as well as for a space application, that's a way that you could facilitate things. But there isn't a reason to have radiation-hardened computers here on Earth, right? You only need that for space. So I think part of the challenge is the space environment is so difficult that Earth-based applications don't necessarily have to design to those conditions. But maybe if the aerospace sector takes off, if the space exploration sector takes off, there's probably more of a need to develop these things, right? Because you don't want to be limited to this megahertz level processor. So I hope, because now I feel like space exploration is becoming more of like a universal thing across a variety of different sectors, that might help to say, well, I'm going to make my new computer, but I'm also going to make it so that it could be used in a space type environment. So that would be my only suggestion. It's a good question, though. So the question is, for the Mars 2020 rover, does it have a helicopter on board, a drone on board, and what's the status of that? And so it does. And so that is a technology demonstration mission. So it isn't, so there's always a baseline set of scientific objectives that you have to meet. Because it's a brand new technology development, nobody's developed a Mars helicopter before. It's a little helicopter. It's like, about this big. It is a technology demonstration as opposed to a requirement for the Flora science mission. But it will get amazing scientific data over a much larger area. So it is being developed. It's a huge technology challenge because the atmospheric density is really, really low on Mars, 1% of what it is on Earth, which means that the thing can't weigh anything, right? So in order to get good enough lift to weight ratio, and it has to have very large span for its helicopter blades and weigh almost nothing. So there's a huge technology challenge literally because of that mass limitation, which then couples to a power limitation, which then couples to a how much science can I actually do limitation. But it is going to happen, and it's going to happen as a technology demonstrator for the very first time. But you can come up with so many different mission concepts where it's true that we've been doing these big fat rovers for each mission. Maybe we don't need to do that at all. Maybe the next mission is just a suite of 8 drones, right, that get released. And then you can spend more money to have something which has an even larger wingspan, or not wingspan, but like you could have an airplane too. It doesn't have to be a helicopter. But it's because of these technology demonstrations that we do each time incrementally, we're able to do more on the next mission. But it is going to happen, and I have friends who are working on it, and it's really cool.
Software and open source and available. Like if you go like software.nasa.gov, you can actually find a whole bunch of like automation systems and what did you mention, like just available for anyone to kind of use and whatnot, play with. Would say someone, for example, thinks as is a software community, refactoring some of that code or whatnot, or kind of optimizing that to make it more efficient, would that be something that can actually help with the Mars One program, for instance?
I would say absolutely yes, because the interesting thing is that the software field is a field where it's actually very hard to find software people to work at NASA because they have so many other options available to them which pay a lot better. So if the software community wanted to help improve code from that perspective, from an efficiency perspective, I'm sure that would be welcomed. I don't know like what the actual mechanism for that is, but what I would suggest is to attend conferences where these things are discussed, see what the state of the art is right now, see places that you could potentially help, and then go directly to whoever's making that presentation and say, and try to influence things in terms of, maybe we can work together, maybe I can make this better. I will say my background is I'm more of an experimentalist, I'm more of the aerodynamic side of things as opposed to the software development, but for sure, the space program is like, probably a decade to 2 decades behind where we are in commercial software activity just because of the bandwidth limitations of the flight computer. But if you could come up with a way to, time's going off, but if you can come up with a way to make anything more efficient, I think that would be welcome.
Cool, thank you so much.
So any idea of using your understanding and any studying to eliminate the problem in Earth, civilization, the barren land of the Earth, or the providing solution to the Earth's problem? So your understanding about the planet Mars and your program about planet Mars, any idea of using those understanding to eliminate the problem of the planet Earth?
Well, that's a really interesting one because we don't know why Mars experienced what it experienced. The theory is that the core was fractured, right? And because the core was fractured with this impact, it disrupted the magnetic field, the atmosphere was ripped away. So there's that element of its planetary climate change that hopefully that doesn't happen here, that'd be pretty bad. But what I could say is that when you design something for space use, you have to design it to be mass efficient, power efficient like you can't believe, and cost efficient, as hard as that may be. There's a lot of cost associated with doing testing and things like that for a space environment. So if we could apply those same principles to how we operate our vehicles here, right? When we operate our vehicles here on Earth, we have no limit to how much power we can consume. That's a terrible thing, right? So if we instituted regulations at the government level, which people are trying to do now, right, which is that you can't use gasoline, it has to be electric, it has to have a certain efficiency level, it has to have a mass per unit length, you could implement those kinds of design approaches and those design standards to make things more efficient, which by definition then helps us here at Earth, right? Because if we're not releasing CO2 emissions, for example, right, if we're reducing the greenhouse gas burden on the planet, we're helping our home here at Earth. But many spacecraft technologies have a direct implication to the economy here on Earth, right? So you take a look at the entire telecommunications sector, like the internet, all of that came from the space program, which then actually helps us here at Earth in terms of generating new jobs and different economic sectors. So there's a huge link between the space program and that, but ways that we could do a better job of protecting our home, it's probably more about an engineering design philosophy, which I would love to see everybody implement even in their daily lives, right? Like just not generating as much waste, right? It's that. So on the space station, for example, this is a perfect example actually. On the space station, every single bit of waste is reused if possible, right? So your urine gets turned back into water. Your feces gets freeze-dried, get the water out, right? You could use that, for example, to fertilize plants. So those kinds of approaches to an environmental control system where you do everything possible to minimize waste, everything possible to maximize reuse, there's no reason why we shouldn't implement that here at home. If we all did that tomorrow, right, in our daily lives, it would have a huge impact, right? You wouldn't have as much stuff going to landfills. So those are the things that I think you can take the lessons of the space program to help us here at home. That was a great question. Thank you. So the question was the radiation levels that we've detected on the surface of Mars, what effect does that have on avionics? So it does have an effect. And so what happens is you have high energy particles which can come in and basically flip bits, and sometimes it can even burn out components. And so when you have a space-rated design to your command and data handling system, your flight computer, it actually has to be designed to be able to handle these high energy impacts. Sometimes there's redundancy. It's inside of metallic shielding, for example. So avionics can handle it in the sense that you can actually design systems that can tolerate a certain amount of energy input, but sometimes you get high energy particles which are too intense. They can actually fry things, and at that point you have to have redundancy. So for our vehicle, we actually have redundant flight computer, so that hopefully the probability is low that it would hit both of them. And so if you lost something on one computer, it was a really bad day on Mars, you can shift over to the other computer. And that's actually happened. Now, normally those can be healed by rebooting, so it doesn't really fry everything. But then you reboot, then you go to the other computer, and you operate on that one until the next one reboots, and you bring it back up again. But the radiation level on Mars is actually pretty benign from an avionics perspective. compared to Jupiter, for example. So Jupiter has a radiation environment which is probably 3 orders of magnitude worse. There's no chance anything could survive like on the surface of Jupiter and orbit around Jupiter because it's that bad. So there, our avionics only last for a couple of months and then they die. So, but on Mars, the radiation environment is tolerable to radiation-hardened computer equipment, which has an analog for other applications on Earth with the military, for example. That's the only analog that exists. So that can be done. So the harder thing is organisms, because when that energy hits DNA, for example, it will you destroy the DNA, you get cancer. But at the same time, we know that we can attenuate it by having a water shield, potentially. You can attenuate it by having going underneath the ground, and then you may also be able to use like polyethylene materials, which are also organics, hydrocarbons, as a shield. But that work has to be done to verify that those things will actually work and protect people, and that's what's underway. Or more money and time needs to be spent on that. So it's an active area, but the avionics part is a little bit easier.
Hi, sorry, just a few more questions here. Now, if you look at just a theory here, now I think you're aware of the Anthropocene period, yeah. Now, is it possible to argue and say that Mars is like a future of the Earth? Are we looking at the future, and when we look at Mars, we're looking at the future of Earth, considering the rate in which human civilization is going? Like I remember reading a few years ago saying that if human civilization were to go like this, they'd last maybe like 240 years, something like that, and then that's it. Because at this rate, it's going to really like unbearable and unlivable, basically.
So it's probably more the case that Venus is a better analog, just because the reason why Venus has its high surface temperature and high surface pressure is because it experienced a runaway greenhouse gas effect, and when that happened, its oceans boiled, and once its oceans boiled, it went up into the atmosphere, which created this high pressure, and then created all these clouds, which basically allowed radiation to come in but not escape. So Venus is an example of like what could happen if you, as a planet, experienced a runaway greenhouse gas effect. I mean, to say that that's a direct analog to Earth, I can't say that, but nevertheless, you can see what happened on a planetary level, and we don't know how that happened to Venus. We have no idea, actually. And so there is an interest to send vehicles to orbit Venus again and also go down to the surface of Venus to collect more data. But I would say that Venus is an analog of what can happen to a planet that experiences a runaway greenhouse gas effect. And we know we're experiencing climate change here because of an increase in greenhouse gases in our atmosphere. That's a fact. So that would probably be a more scary alternative, actually, because that one you can't do anything about. Mars one, I suppose, as long as you had the ability to create little habitats in which you could live, you could survive it. But Venus, that's impossible.
What are your thoughts on asteroid mining, and where do you see the feasibility of that coming into as a resource collection facility and a mechanism to make things more economical? Like, where do you see that in the timeline compared to Mars colonization?
I don't, that's a good one. So there are a few private companies who are looking at asteroid mining, and so landing on asteroids is actually relatively easy because they have no gravity well. You have to be able to stick, which is harder, but even that's a little bit simpler. So I think for that to become useful, probably be when we decide to do in-space assembly. And so if you did in-space assembly and then you were able to get raw materials from space, then that would be a really smart thing. Would it facilitate something like a mission to Mars if you were able to mine fuel, for example, or something that could serve as a precursor to fuel, like water, for example, right? So launch vehicles use liquid hydrogen, liquid oxygen. That's incredibly efficient chemical reaction. So if you were able to mine H2O from asteroids, hydrolyze it, create liquid oxygen, liquid hydrogen in orbit, you could imagine having fuel depots, for example. So we're not there yet in terms of having the need for an in-space infrastructure, but you'd be crazy not to use something like that when we finally do get to the point as a society where we have people transiting in our solar system all the time. Then you wouldn't want to put yourself in a gravity well, come back out of it for no reason if you can get a resource sitting around in a low gravity environment. So, but I think I should probably close it off now. So thanks very much.